Grounding of an ungrounded diesel generator is crucial, but these generators are often operated and grounded to prevent damage to the generator windings in case of a line-to-ground fault in the main power system. Ungrounded generators require a ground fault detection system to indicate ground faults and allow for safe shutdown. This system typically uses a sensitive relay that measures the voltage difference between the generator neutral and ground. The type of grounding system to use depends on the specific requirements and regulations. One option is resistance grounding, where a resistor is connected between the generator neutral and ground. This limits the fault current and helps protect the generator from overcurrent damage. Another option is reactance grounding, where a reactor is connected between the generator neutral and ground. This limits fault current but allows for quick tripping of the generator in case of a ground fault. Protection of an ungrounded diesel generator is paramount. The generator should be protected against overcurrent faults by using appropriate overcurrent protection devices such as fuses or circuit breakers. The ground fault detection system should trigger the appropriate protection devices, for example, generator shutdown, to prevent damage to the generator. Anti-islanding protection is essential to prevent the generator from continuing to operate in parallel with the main power system if a grid outage occurs. This protection system detects a loss of grid power and disconnects the generator from the system. Considering the grounding aspects, the grounding system requires a proper earthing electrode, such as a ground rod or grid, to provide a low resistance path to ground. The grounding resistance should be low enough to ensure effective fault current flow and tripping of the protection devices. All metallic parts of the generator and associated equipment should be properly bonded to the grounding system. It is also important to perform regular maintenance and testing of the grounding and protection systems. Coordinate with the utility company to ensure proper coordination of the grounding and protection systems. Follow all applicable codes and standards, for example, National Electrical Code or NEC, Institute of Electrical and Electronics Engineers or IEE. Consult with a qualified electrical engineer for specific design and installation recommendations. Delving deeper into grounding, it's important to consider different grounding methods for the generator neutral. Solid grounding, where the neutral is directly connected to ground, provides the lowest impedance path for fault currents, leading to quick operation of protective devices. However, it also results in high fault currents, which can cause significant equipment damage. Resistance grounding introduces a resistor between the neutral and ground, limiting the fault current to a predetermined value. This reduces stress on equipment and minimizes voltage dips during ground faults. High resistance grounding uses a higher resistance value, further limiting the fault current, often to just a few amps. This approach is commonly used in systems where continuity of service is critical, as it allows for continued operation during a single ground fault. However, it requires sensitive ground fault detection to identify and locate the fault. Reactance grounding, as mentioned earlier, utilizes a reactor to limit fault currents. The choice between these grounding methods depends on factors such as the size of the generator, the system voltage, the desired level of fault current limitation, and the need for service continuity. Regarding overcurrent protection, fuses are simple and cost-effective devices that provide overcurrent protection by melting when the current exceeds a certain level. Circuit breakers, on the other hand, are electromechanical devices that trip and interrupt the circuit when an overcurrent is detected. Circuit breakers offer the advantage of being resettable, allowing for quick restoration of power after a fault. Overcurrent relays are used in conjunction with circuit breakers to provide more sophisticated overcurrent protection. These relays can be programmed to respond to different types of overcurrent conditions, such as short circuits and overloads, and to coordinate with other protective devices in the system. Ground fault protection is another critical aspect of generator protection. Ground fault relays are used to detect ground faults by monitoring the current flowing in the grounding conductor. When a ground fault is detected, the relay trips a circuit breaker to isolate the generator from the system. Differential protection is a more advanced form of ground fault protection that compares the current entering and leaving the generator windings. If there is a significant difference between the two currents, it indicates a fault within the generator itself, and the differential relay trips a circuit breaker to quickly isolate the generator. Anti-islanding protection is crucial to prevent the generator from operating independently from the grid during a grid outage. Loss of mains relays are commonly used to detect a loss of grid power by monitoring the voltage and frequency of the grid. When a loss of grid power is detected, the loss of mains relay trips a circuit breaker to disconnect the generator from the system. Reverse power relays are used to prevent the generator from feeding power back into the grid during a grid outage. These relays monitor the direction of power flow and trip a circuit breaker if power is flowing from the generator to the grid. Rate of change of frequency relays are used to detect a sudden change in frequency, which can indicate a loss of grid power. When a sudden change in frequency is detected, the rate of change of frequency relay trips a circuit breaker to disconnect the generator from the system. Grounding considerations are essential for ensuring the safety and reliability of the generator system. The earthing electrode, such as a ground rod or grid, provides a low resistance path for fault currents to flow back to the source. The grounding resistance should be low enough to ensure effective fault current flow and tripping of protective devices. The National Electrical Code, specifically Section 250.56, specifies the maximum allowable grounding resistance for different types of systems. Bonding is the process of connecting all metallic parts of the generator and associated equipment together to create a low impedance path for fault currents. Bonding helps to prevent voltage differences between different parts of the equipment, which can be a shock hazard. Additional recommendations include performing regular maintenance and testing of the grounding and protection systems to ensure that they are functioning properly. This includes visual inspections, insulation resistance tests, and functional tests of protective devices. Coordination with the utility company is essential to ensure that the grounding and protection systems are properly coordinated. This helps to prevent nuisance tripping and ensures that the generator is properly protected in the event of a fault. Following all applicable codes and standards, such as the NEC and IEE standards, is essential for ensuring the safety and reliability of the generator system. Consulting with a qualified electrical engineer for specific design and installation recommendations is highly recommended. An electrical engineer can help to assess the specific needs of the application and design a grounding and protection system that meets those needs. Consider the generator neutral grounding resistor sizing. When using resistance grounding, the size of the grounding resistor is crucial. It must be selected to limit the ground fault current to a safe level while still allowing for reliable detection and tripping of protective devices. The resistor's ohmic value is determined by the system voltage and the desired ground fault current. The resistor's wattage rating must be adequate to withstand the continuous current during a ground fault without overheating. Ground fault detection methods must be considered. Several methods exist for detecting ground faults on ungrounded or high resistance grounded systems. One common method involves measuring the neutral to ground voltage. During a ground fault, the neutral voltage will shift, and this voltage change can be detected by a sensitive relay. Another method involves using a ground fault current transformer, which encircles all the phase conductors and the neutral conductor. During a ground fault, current will flow in the grounding conductor, and this current can be detected by the current transformer. Selective coordination of overcurrent protection devices is important. Selective coordination ensures that only the overcurrent device closest to the fault trips, minimizing the impact on the rest of the system. This requires careful selection and coordination of fuses, circuit breakers, and overcurrent relays. Time current curves are used to coordinate overcurrent devices, ensuring that the device closest to the fault trips first. Surge protection devices, or SPDs, are critical for protecting the generator and associated equipment from voltage surges caused by lightning strikes or switching operations. SPD should be installed at the generator terminals and at other critical points in the system. SPD work by diverting surge current to ground, protecting the equipment from damage. Regular testing of SPD is essential to ensure that they are functioning properly. Insulation monitoring devices can detect insulation degradation before a fault occurs. These devices continuously monitor the insulation resistance of the generator windings and provide an alarm if the insulation resistance falls below a certain level. This allows for proactive maintenance and prevents unexpected generator failures. Proper grounding of the generator enclosure is very important. The generator enclosure must be properly grounded to provide a low impedance path for fault currents. This helps to prevent voltage differences between the enclosure and ground, which can be a shock hazard. The grounding conductor should be sized according to the NEC, specifically section 250.122, based on the size of the overcurrent protection device. Consider the impact of harmonics on grounding and protection. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads such as variable frequency drives or VFD in electronic equipment. Harmonics can cause overheating of equipment, increased losses, and interference with sensitive electronic devices. Harmonic filters can be used to reduce the level of harmonics in the system. Reviewing the NEC Article 700.12 pertaining to legally required standby systems is very important. This section provides requirements for the installation and operation of legally required standby systems, such as those used in hospitals and emergency facilities. It covers topics such as transfer switches, overcurrent protection, and wiring methods. Emergency power-off or EPO switches should be installed in easily accessible locations to allow for quick shutdown of the generator in case of an emergency. EPO switches should be clearly labeled and readily accessible to authorized personnel. The generator control system should be designed to provide reliable and safe operation. The control system should include features such as automatic startup, automatic shutdown, and fault annunciation. The control system should also be designed to prevent the generator from operating outside of its safe operating limit. For detailed understanding of grounding and bonding, read the NEC Article 250. This article provides comprehensive requirements for grounding and bonding of electrical systems. It covers topics such as grounding electrodes, grounding conductors, bonding jumpers, and equipment grounding. Understanding and complying with the requirements of NEC Article 250 is essential for ensuring the safety and reliability of the electrical system. It is important to consult with a qualified electrical engineer to ensure that the grounding and protection system is properly designed and installed. A qualified electrical engineer can assess the specific needs of the application and design a system that meets those needs. They can also provide guidance on selecting the appropriate equipment and ensuring that the system complies with all applicable codes and standards. Generator load bank testing should be performed regularly to verify the generator's performance and ensure that it can handle the expected load. Load bank testing involves connecting a resistive load to the generator and measuring its voltage, current, frequency, and other parameters. This helps to identify any potential problems with the generator before they cause a failure. The transfer switch selection is an important aspect of standby generator systems. Automatic transfer switches, or ATS, are used to automatically switch the load from the utility power to the generator power in the event of a power outage. Manual transfer switches require manual operation to switch the load from one source to another. The selection of the transfer switch depends on the application and the desired level of automation. Consider paralleling generators for increased capacity and redundancy. Paralleling generators allows for increased capacity and redundancy. However, paralleling generators requires careful coordination of the control systems and protection systems. Synchronizing equipment is used to ensure that the generators are operating in phase before they are connected in parallel. Proper grounding and protection are essential for the safe and reliable operation of parallel generators. Always use a qualified electrician for installation and maintenance. Electrical work should only be performed by qualified electricians who are trained and experienced in the installation and maintenance of electrical systems. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent accident. Always follow safe work practices and use appropriate personal protective equipment. Remember to keep detailed records of maintenance and testing. Maintaining detailed records of maintenance and testing is essential for tracking the performance of the generator and identifying any potential problems. Records should include the date of the maintenance or testing, the work that was performed, and any findings or recommendations. This information can be used to improve the reliability and performance of the generator. The generator set should comply with local codes and regulations, and the installation must comply with all applicable local codes and regulations. This may include requirements for permits, inspections, and specific installation practices. It is important to consult with the local authorities to ensure that the installation complies with all applicable requirements. Regularly inspect the generator set for any signs of damage or wear. Regular inspections can help to identify potential problems before they cause a failure. Inspections should include checking the fluid levels, belts, hoses, and wiring. Any damage or wear should be repaired promptly. Proper ventilation is essential for the generator set. Generators produce heat and exhaust gases, so proper ventilation is essential to prevent overheating and the buildup of dangerous gases. The generator should be located in a well-ventilated area, and the exhaust gases should be vented to the outside. Also, ensure proper fuel storage and handling for safety. Fuel storage and handling should be done in accordance with all applicable codes and regulations. Fuel should be stored in a secure location, away from sources of ignition. Fuel handling should be done carefully to prevent spills. Spill containment measures should be in place to prevent fuel spills from contaminating the environment. Train personnel on proper generator operation and maintenance. Training personnel on proper generator operation and maintenance is essential for ensuring the safe and reliable operation of the generator. Training should include topics such as starting and stopping the generator, performing routine maintenance, and troubleshooting common problems. Trained personnel are better equipped to operate and maintain the generator safely and effectively. A well-maintained and properly protected diesel generator is a valuable asset for any power plant. By following the recommendations outlined above, the reliability and safety of the generator can be ensured. This can help to prevent costly downtime and ensure that the power plant can continue to operate safely and efficiently. For instance, the National Fire Protection Association, or NFPA 110, provides standards for emergency and standby power systems. NFPA 110 outlines the requirements for the installation, maintenance, and testing of emergency and standby power systems, including diesel generators. Compliance with NFPA 110 is essential for ensuring the reliability and safety of these systems. Remember to consider the environmental impact of the generator set. Diesel generators can produce emissions that can have a negative impact on the environment. It is important to select a generator that meets all applicable environmental regulations. Emission control devices, such as catalytic converters, can be used to reduce emissions. Regular maintenance and testing of the generator can also help to minimize emissions. Also consider cybersecurity for generator control systems. Generator control systems are increasingly connected to the internet, which makes them vulnerable to cyber attacks. It is important to implement cybersecurity measures to protect the control system from unauthorized access and control. This may include using firewalls, intrusion detection systems, and strong passwords. Regular security audits should be performed to identify and address any vulnerabilities.